Okay, welcome back. In this video, we will be talking about Boolean data type and Boolean operators. So let's get started. In my first presentation about data types, I talked about Boolean expression, and I mentioned that Boolean is named after George Boole, who described an algebra composed of based only on zeros and ones, and they are used to represent false and true respectively and effectively, and hence the name Boolean. So again, when we say Boolean, we mean a value that is either true or false. Okay, so do you remember this slide? Today we are going to take the next bunch of operators after arithmetic and assignment. We talk about those: comparison, membership, identity, and logical. All of them are collectively Boolean operators. That means they return Boolean values. But before we talk about we dig in Boolean values, I just want to get your head start about the ASCII table, so that our the next of our video will be easy. ASCII table, if you ever heard this word, was created because in computer early days there were a struggle, a pain to integrate data from different vendors, say IBM, Motorola, etc. Everyone writes data in a different format. So they finally came to standardize the codes of encoding characters and letters and other symbols into what's called American Standard Code for Information Interchange. And the acronym for this is ASCII. In the ASCII, everything is a symbol, and the symbol is assigned to a value in the range of, from zero, in the period from 0 to 155. That includes numbers, capital letters, small letters, and other control characters, symbols, etc. Here I am showing some of the ASCII entries, the most famous and interesting entries. So here I see the value and the value in decimal and hexadecimal system. The decimal is the one we know. The hexadecimal you will study later. But I want you to remember some numbers that will help you throughout your computer science journey. The space here is at 20 hexa, which is 32 decimal. So the space is number 32. The one here I'm talking about the one as a symbol, the symbol which writes one, not the value one. The symbol one is assigned the hexadecimal 31, and the capital A is to the hexadecimal 41, the small a is 61. So we have A, B, C, D, E, F, G capital and A, B, C, D, E, F, G small. This is starting from 41 and it's starting from 61. This the difference between 40 and 60 is 20, and 20 is the number of the space. So if you remember, space, capital A, small a, you can map any number, any other character with a capital or small to it. And the numbers are also from 30 hexadecimal and going downwards. So 30, 31, 32, 34, etc. So 0, 1, 2, 3, 4, 5, 6, 7, 8. This is what we need to know about the ASCII table. So at the end of the day, every symbol is a number. Every symbol is represented by a number. And so every string of name or whatever is a sequence of numbers. So, for example, the name Amr, which is my name, is a sequence of numbers 65, 109, 114. 65 is capital A, which is 41 hexadecimal, and then small m and r are down here somewhere in the table I didn't show. So if this is 101, go down to 109, you will find m, 114 will find r. So again, bottom line is that everything is a symbol, and the symbols are and the strings are sequence of symbols, which means sequence of numbers. Sequence of numbers. Remember this. Okay, back to the Boolean operators. The Boolean operators, we have these four groups: comparison operators, membership operators, identity operators, and logical operators. Comparison operators have the very simple meaning, as we know in arithmetics: greater than, less than, greater than or equal, less than or equal, equals or not equals. And they follow the natural order of values and the lexical order for the strings. So A comes before B, before C, etc. Next group is the membership group. They have two operators, in and not in. They test this test whether an item or subsequence, the item is present in a collection, or subsequence is present within a sequence. We'll come to examples very soon. The third is identity, which tests whether the two items are exactly one and the same object. So we have is and is not. It's not a good idea to use not is. There is a dedicated operator called is not. Finally, we have logical operators, and, or, and not. And or combine two Boolean expressions, and not negates an expression. Let's talk about them in detail. So some simple values. We have one the expression 1 greater than 0. This is true. 1 equals 1 is also true. 1 greater than or equal 1 is true. 1 greater than 1, this is not true, so it's false. 7 doesn't equal 7 is, of course, it is false. Okay. Now, if you want to use is and is not, none is none. This is true. And here it's important to remember that we should not use the equal operator when we compare the non-value. We use the is and is not operator, because none actually is a type, is not only an object, it's also a type. A sequence 1, 2, 3, when you compare it to none, so 1, 2, 3, it's an object, and of course there is something. So none, we said earlier, represents null. So an object is not null. So this is also true. And again here we use is not to compare with the value none. It's nice to note here that when we compare something to none, we don't although it's a collection, we don't compare its items, it's compared the object itself. So it's one value. That's why we use is none, not or, not are none. Okay. That's why I included this sequence 1 to 3 within the symbol values. Now, doing the same operators or similar operators on sequences, the comparison of the operators is done on sequences. They are done element by element. So 1 to 3 comparing to 1 to 4 is done 1 against 1, 2 against 2, and then 3 against 4. If 1 equals 1, goes the next, 2 equals 2, goes the next, 3 is smaller than 4, so the whole sequence is smaller than the whole sequence. Similarly, 5 to 3, is it smaller than or equal to 1 1 1? Although okay, now we know we start with 5 compared to 1. Starting 5 comparing to 1, 5 is not smaller than or equal to 1. So the whole sequence is greater than actually the second one, so the whole expression is false. Now let's do it again on strings. Strings, as I said, are sequences. So A B C, capital A B C, compared to capital A B C, they are actually equal because A is equal to A, B equal to B, C equal to C. So the description is true. A B C is it less than A B D? So let's see, A equals A, B equals B, C is smaller than D. So the whole expression is true because C is smaller than D. Now Z B C in comparison to A B C, we know that Z is greater than A. So if we compare them using smaller than or equal, so this expression is false. And when all elements are exhausted in one of the operands, the longer sequence is greater. So we have 1 2 3 4 compared to 1 2 3. The first 3 operands here are equal to 3 operands here, and there is one operand, one element extra in the first operand. So the one with more elements is greater than the one which has been exhausted already. So comparing with greater than, this is true. Okay, now testing with whether an element or a subsequence is in a collection or a sequence. BCD is already present in A, B, C, D, E, F, G. Yes, that's correct. So this is true. Is 5 present in 1 to 3? No. So 5 not in 1 to 3. This is true. Next is the logical operators. Logical operators are used to combine logical expressions to produce compound logical expression. We have the 3 reserved words and, or, and not. And produces true when both operand A and B are true, false otherwise. Or is false when both A and B are false, true otherwise. So it means if one is if A is true, then both are true. If B is true, both are true. If both of them are true, also the expression is true. And this is a little tricky. We'll talk about very in 2 lines. The third is not negates a single input. So if a true becomes false and false becomes true. Now it's important to notice that the operator which produces true when only strictly one of the operands is true, strictly is true, this is called XOR. This is used when which means exclusive OR, which we use when we say I will go right or left. I cannot go on both sides. I cannot go on both sides at the same time. So I go right exclusively or left. But in the normal OR, which is what we hypothetically mix with XOR, means the first or the second or both. XOR means the first or the second. Okay, we'll come to examples. The first, no, so some examples of the AND first. The expression can order taxi is the combination of I have phone and I have internet. If I must have both of them in order for the variable can order taxi to hold the value true. If only have internet but have phone but no internet, this is not going to be combined to true. Similarly, should wear sunscreen is only when it is sunny and I will be outside. If I'll be outside but it's not sunny, I don't need sunscreen. If it is sunny but I'm going inside, then I don't also need to wear a sunscreen. If both it is not sunny and I am not outside, of course I will not need sunscreen. So I need sunscreen only in case the first and the second are true. Okay. We can start a meeting when the host is present and all required attendees are present. If the host is not, if any of them is missing or both of them are missing, then the whole expression evaluates to false. Wi-Fi is available if both Wi-Fi is on and the router is working. If the router is not working, if the Wi-Fi is not on, then the Wi-Fi will not be available. I can do workout if I have no injuries and I have free time. So if I have a hand like this, I can do workout on my hand. I have to wait, or if my hand is free but I don't have free time, I cannot do workout. Okay, now next are examples of or, which means one or the other is enough, not exactly or both of them. So I should go for shopping if the fridge is empty or I have guests coming. Of course, if both of them are true, I will also go for shopping. Meeting should be online. If there is a remote team or there is bad weather. So even if we are all from the same city but bad weather, like currently, we should make the meeting online. If the team has remote members, it must be online. If both of them must be online. So or means the first, the second, or both. Similarly, should enable silent mode if I am in a meeting or in cinema. I should leave early if it is rush hour or bad weather or both. I should drink water if I'm thirsty, or he is should drink water if he is thirsty, or it has been a long time since he last drank. I will need extension for my homework when too many deadlines and not finished work. This is an expression. Or medical issues. Now we're making it a little complicated. So if I have medical issue, I need extension. If I have too many deadlines, but I finished work already, this is not enough to make the left side of the OR operator true. I should sleep if I'm tired and time after midnight, or I have an early meeting. So if I'm not tired, okay, I can stay awake. If it's still early, but I have meeting, early meeting. I still need to go. This right side will be true, so I have to sleep if I'm also tired. Okay, next is expressions of not. The first expression will explain the idea of not. I should start CPR if heart is not beating. So if heart is beating, which if heart beating is true, I should not start CPR. If heart beating is false, I should immediately start CPR. So if input is true, the output is false. Input is false, the output is true. I need a jacket if it is cold and I don't have jacket. So if it is cold but and I have jacket, it will now we have true at on the left side. If I have jacket, it will be if I if this is true, negating it will make it false. So it will be true and false. I will not need a jacket because I have one already. If I do, if have jacket is false, false of false is true. It means I have jacket is false. It means I don't have a jacket. Don't have a jacket. Negating it became true. And cold is true. So true and true is true. I can go for swimming if it is hot and not pool closed. If pool is closed, if this is true, putting it make the right side false. So true and false, or whatever and false, will be false. Mr. XYZ is late to class if class started and not already in class. So if he's already in class, this is true. Adding not, making the whole expression not, and adding it to and will make the whole expression false. Which means he is not late to class because he's already in the class and although the class started. Student can submit assignment if no deadline passed and homework deadline passed and homework finished. So homework is finished already, but deadline must not be false. False. Passed must be false, which means the deadline is not yet passed, so that this becomes true, and true is true will become true. Again, and it could trip if the destination is cold and not staying indoors. Not staying indoors. I can board the plane if I have the ticket and have a passport and not gate closed. If the gate closed, everything will be, if this is true, negated become false and everything will be false. So I cannot board the plane. Finally, I will need a grocery if the fridge is empty and not already ordered. If I order already, then I don't need to go to the grocery. Okay, let's do some more complex expressions. So should take train equals car is unavailable or heavy traffic and the train is running. So that means if the car is available, I just sorry, if the car is unavailable, then I have no choice. I have to take a train. If the car is available, but both of other conditions, both of them are true because they are linked by and. heavy traffic and the train is running, then in this case I would prefer to take the train. If traffic but no trains, I have no option. If train is running but no heavy traffic, so I would not prefer to take the train. I prefer to drive. So if the car is not unavailable, which means car is available, then I will still uh, take my car. Can drive today. I can drive today if I have driving license and car not broken and I'm not too tired. Notice here something interesting about the operator precedence, which I talked about earlier, that all unary operators have a um, higher operator precedence than binary operators. So not not too tired and not car broken. I don't need to put parentheses around them because it's already understood that not being a unary operator is um, uh, of higher priority than any binary operator. So it works directly on the operand next to it. I mean, yes, following it. So I can drive today if three expressions conditions are true. If I have the valid driving license and car broken is false, which means which means car is not broken, car is working, and not too tired, which means I'm not too tired, which means I am uh, awake or healthy. So if the three of them are true, true, and true, and true, in this case only I can drive today. If any of them is false, I will not. So I can pay if I have um, cash or working card, and the card is not blocked. No, not blocked. Sorry, this is wrong. I have to fix it. So I fixed it. Last one is I can pay if I have cash or I have a card which has both conditions true. It's working and not blocked. So blocked is false. Negated becomes true. So this is true. And have a card, a working card is true. Both these are true. Joined by and is true. Or has cash. So I hope you understand now. And or and not in a complex in a simple and a complex context. To summarize here, we what we show here is called the truth table of the logical operators and or and not. And when it is a binary operator that takes a and b, if a is true and b is true, the result a and b is true. Otherwise, anything else, the result is false. So true when both a and b are true, false otherwise. For the or, um, it all of them are true except only the case where both of them are false. So false when both a and b are false, and true otherwise. Not is a unary operator that when takes true becomes produce false, when it takes false produces true. Finally, I gives you some notes. Comparison. Any comparison cannot be done between operands of different type. So you cannot compare a Boolean to integer. or float to map, uh, whatever, except for one exception, which is comparing integer to float. Actually, under the hood, the integer is promoted to a float, so it becomes float to float, which is uh, still following the format, the rule, and then we can compare. So only integer and float can be compared together with different types based on the condition that the float is promoted to integer. Sorry, the integer is promoted to float underneath, under the hood. Another interesting note, methods that return Boolean values usually start with the prefix is. So something like is digit, is alpha, is upper, is instance. So when you find, when you see a method for the first time that starts with is, most probably it returns a Boolean value. However, that doesn't mean that uh, all Boolean values start with is. Some of them don't simply start with is. Okay. Uh, Next, I want to say that the Boolean expressions are used when are used to make decisions. They are called conditions. So conditions can be used to make decisions like choosing between options or controlling loop, which we'll see in the next video, inshallah. One interesting, very interesting and important note is that and or are short circuit operators. What does that mean? Remember short when you have a battery and a lamp, and then you make a short circuit between the two sides, positive and negative. So the electric current goes through the short circuit and doesn't go to the lamp. Is exactly the situation here. So let's consider two Boolean values, bool 1 and bool 2. Say we call them A and B, whatever. Consider expression bool 1 and bool 2. So if bool 1 evaluates to false, we know that and produces true only in case both of them are true. So if the first one is false, the operator doesn't even bother, doesn't evaluate bool 2. It returns false directly without evaluating the right hand side operator, the right operator. Similarly, with OR, we know that OR produces false in case uh, uh, both of them are false. Anything else, it will produce true. So um, if the first operand is true, the OR already knows that it will, the whole operation expression will be true, so it doesn't evaluate bool 2. Instead, it returns quickly. Okay. There, there is a very famous and very critical application of this rule or this feature, which is preventing wrong or erroneous or error-prone, yes, error-prone operations like division by zero. So, for example, when you want to avoid division by zero, you start by writing the expression to check whether denominator does not equal zero, and then the expression which divides the first by the second and puts the value to the left side. So if the denominator is zero, uh, only in this case, in this case, the other side we know will not be evaluated at all. So that will prevent us from falling into exceptions and other stuff. Next slide or two is about simplifying expressions. This is not so important for you now, but it's nice to know. Put them in your mind for the future. You can use rules to or tricks to simplify long and lengthy expressions into smaller expressions. For example, a student is graduating student if his grade equals 5 or 8 or 12, which means he will be graduating from the elementary, middle, or high school. So graduating equals grade equal 5, or grade equal 8, or grade equal 18. We can replace this complex expression with simple expression. Graduating equals grade in a collection or a sequence containing 5, 8, and 12. That's all. That's simple. You see, short, listen in operator overhead, in calculation overhead. Another another form. Um, Student is in a middle school if his grade is greater than or equal to 6 and less than or equal to 8. Python has a unique method of writing joining expressions in a way. You can say middle school equals 6 less than or equal to grade less than or equal to 8. So we compared, we not compared, sorry, we combined the two expressions with and into one expression with two operators, actually, two operators and three operands. Very nice, isn't it? Python is really nice and easy. And the other way around, now, I want to give a discount for young kids and seniors. So discount equals is only available when age is less than or equal to 10 or greater than or equal to 16. So this is one operator, second operator, third operator. We can simplify this operation into discount equals not age is greater than 10 or less than 16. Also, an interesting point to consider, which is that the opposite of smaller than is not greater than. Not smaller than is greater than or equal. And to explain this, let me tell you. What is the opposite of yesterday? The answer is today. Okay. What is not yesterday? Sorry. What is the opposite of the best? It is the future. Okay. But what is not the best? It is present or future. I want you to understand this difference. So if some what is the opposite of the best? It is future. What is what is not best? It is present or future. Similarly, what is we have positive numbers, negative numbers, and we have zero. So being not negative doesn't mean being positive. It means zero or positive. Okay, same here. So discount is given to age less than or equal to 10 or age greater than or equal to 60. The opposite of this is not smaller than, not smaller than or equal, and smaller than, not smaller than or equal. Okay. Last and not least, we can use De Morgan law to simplify conditions, which says that not A and B exactly equals not A or not B. And not A or B is exactly equal to not A and. So let's say, let's give an example of or. Let's say here, not A and B, not A and B. I can travel if the passport is not expired and the visa is not expired. So not A and not B. This can be simplified into not A or B. I can say not passport expired or visa expired. Okay. Actually, don't, it depends on your understanding of the word simplification, which is more simple. But in general, this is a way of converting the expression into a way that can be used later in more complex expressions. Okay, similarly, not A or B. I can drive today if not car broken and not too tired. Or I can say not car broken or too tired. So if the car broken or I am too tired, if any of them is true, the description will be true. Negated will be false, so I cannot drive today. And the opposite. I can drive today only if neither of them is true. So the car is not broken and I'm not too tired. In both cases, uh, so if too tired is true, this will be true. This will be negated into false. I cannot drive today. If the car is broken, this will uh, this will be true. Negated will be false. Then I cannot drive today. Okay. Finally, I will leave you try these exercises. Just print them in the console or put them in a program and check what will the result be. Okay. See you later. Thank you for watching until here.